Um, Hello and good afternoon. Sorry for the delay. Running a little bit late, so just give me a second. Okay, so sorry about that. So we're talking about caches, and the okay. See where. Okay, so we talked about homonyms. Okay. Again, sorry about that. I was running a little bit long, short. What am I saying? Late. Okay, so let's get it started. So we were talking about caches, and then we took a segue to talk about address translation, which was the topic of the previous lectures, and we introduced TLBs, and TLBs are basically caches for address translation. When we translate an address, we just cache it, and to just look at the flow one more time. So basically, when your virtual address is generated, you first go to your TLB to see if this virtual address has been translated to a physical address already. If yes, then you have your address. You just go to your physical memory and you get the data that you want. If not, then you miss in your TLB, and then you have to do a page table walk. That means that you have to go to your page table a couple of times, probably if you have multi-level page table, to get the translation. Once the translation is done, then you probably want to cache that translation in your TLB. And then in case that the translation is not defined, maybe the access is not a valid access, or maybe the PTE is not valid, then you raise an exception. So this was the general idea. The last topic that we discussed was the topic of homonyms, and so this was the issue that we had if we just look at the virtual address and its translation in TLB. Then it could be that we context switch to a new process, and the new process is using the same virtual address, but then this virtual address is mapped to another physical address in the page table, but we don't have that information in TLB. So we had two options: either invalidate the entire TLB every time we context switch, which again was simple, but then it had performance cost in case we go back to the one that we context switched from. Then we have to basically warm up the TLB from scratch, which has performance cost. So an alternative to that was to tag our TLBs with the process ID. And not only we check if the virtual address translation exists, but also if this virtual address is the right virtual address for the process that is running. The other problem that could come up is in multiprocessors. So let's assume that, so in a multiprocessor, each processor has its own TLB. So in this case, let's assume that I have 3 processors in my system. Each one of them has its own TLB. Now, as you can see, I have tagged the translations with the process ID, which is what we talked about in the previous slide. Now, let's assume that processor 1 updates process 0's PTE, right? Let's assume, so this, as you can see in this picture, process 1, process 0 and process 1 have been in the past executed on processor 1 and processor 3. And processor 2 has only been executing process 0. Now let's assume that at some point in time, process 0 is running on processor 1. And then for whatever reason, the operating system decides to update a page table entry for this process. Now, what should happen? Well, obviously, we're going to do whatever we have to do with the page table, with the TLB in processor 1, where the update is happening. But we can't stop at that point, because for process 0 and this particular page, which is this page, 53, I have an entry in processor 2 as well. So this entry for this particular virtual page exists in 2 processors TLBs. So in TLB1 and in TLB2. Now, if I only update TLB1 and leave this one unchanged, then next time that I'm going to run process 0 on processor 2, then I'm going to be having a wrong entry in the TLB. So to avoid this, what happens is we do a shoot down. So what is a shoot down? So shoot down is basically one processor notifying other processors that a page table entry has been updated. Now, when the other processors receive this message, this interprocessor interrupt, they will shoot down this entry. So although this entry was not updated on this particular processor, because this processor got a message from another processor that this page table entry has been updated, it can shoot down that page table entry from its TLB. So this process is a shoot down process. Now, processor 1, which is the initiator of this, where the initial update happened, has to wait for all the processors to acknowledge this shoot down. So it's going to send a message to processor 2, and it's going to send a message to processor 3. Probably processor 3 is going to say, everything is fine. I don't even have that entry in my TLB. So then we're going to wait for processor 2 to do the shoot down and then come back to us with an acknowledgement. Once we have all the acknowledgements from all the processors, then we can continue executing. At that point, we're sure that there is consistency between different TLBs. OK, so what happens if we miss in TLB? Previously, I just said, OK, we're going to do a page table walk. But the question is where this walk is going to happen. So we either do a hardware lookup of the page table, or we do a software lookup of the page table. So this slide is very similar to the slide we saw in the previous lecture, which was hardware versus software translation. So this is basically that same slide, right? Because when you have a miss in TLB, then you have to translate the address. It means that you don't have it cached. So now how do you translate? Well, in most of systems, the hardware starts traversing the page tables. So this is a process that is called page walk. So you start going through all the page table entries to find the page table entry with regard to the virtual page that you're looking for. If you find a valid page table entry, then everything is fine. So you can just update your TLB and continue executing. If you find an invalid page table entry, then you can raise a page fault and get the kernel involved to see what should happen next. In software traversed page tables, in cases where the translation happens in software, every time you get a TLB miss, then you have to invoke the operating system and ask for the translation. So then operating system is going to do the translation and get back to you. So that's pretty much it. So one thing here is that here this page fault does not necessarily mean that you're going to terminate the processor. Terminate the process, because there is a possibility that this is, for example, a heap expansion or a stack expansion, and then the kernel will just fix it up. Or it could be that it's a page that was swapped to disk, and the operating system brings back the page. So it doesn't necessarily mean that the process should terminate. In this one, however, is basically, the operating system gets involved from the beginning, and if operating system recognizes that this is an invalid access to a page, then operating system will just go with that flow. So either fixes it or just terminates the process. Okay. Now let's talk about page table faults, and let's connect that to any sort of exception that could happen in your program. What happens? So exceptions are synchronous. If you remember from early lectures on operating system concepts, we talked about exceptions as a synchronous event that is caused by the program. Now, one example of an exception is divide by 0. So if your program divides by 0, that raises an exception. Another example is this page fault that we just saw, or TLB fault. So these are exceptions that could happen as a result of executing an instruction. Now, in general, with exceptions, if we want to go back and execute the software, if the exception doesn't cause the process to terminate, then where should we go? Where should we go back to the program that raised the exception? So usually you want to go to the same instruction that raised the exception, because you didn't really finish that instruction. That instruction caused an exception, and now you want to re-execute that instruction once the exception is handled. For example, if the instruction was using extra heap that was not allocated, now that it's allocated, you want to re-execute that instruction. Now, what could happen if the instruction that raised the exception has side effects? So what do I mean by side effects? I got a question that is asking if does a page table mean accessing, does a page fault mean accessing invalid memory? Page fault means that the page table entry corresponding to this virtual address was invalid, or the access was not permitted. For example, if you had this translation for read-only and the request is to write to this page, then you get a page fault. So page fault means either invalid or lack of permission. So in both cases, the operating system should take care of it. So if it is invalid, maybe it's because we have swapped it. So maybe we should bring it back and make it valid. If it is permission, then we have to check if we can increase the permission, or if this is an unaccepted permission that should cause the program to terminate. So that's what page fault really mean. Okay, so going back to the discussion we had, we said that we want to, when we get the exception handled, we want to go back and execute the same instruction that caused it. Now the question arises, what if the instruction has side effects? Now I have a bunch of examples here. So one example is push instruction, right? What does a push instruction do? So push instruction, what it does is there's a stack pointer. So it copies the data here 10 on top of the stack, wherever the stack pointer is pointing, and then increases the stack pointer. So first we do a memory write to wherever a stack pointer is pointing, and then we increase the stack pointer. Now, when we increase the stack pointer, so when we do the write, so there is the write and there is the increment that we do to the stack pointer. So these are two separate tasks for a same instruction. What if one of these causes an exception? For example, what if we first increase the stack pointer, so a stack pointer has been increased, and then write, which is basically what usually happens. I think I made a mistake. I said you first write and then increase. I apologize. You first increase and then write. So what if you increased, and when you wanted to write, you realize that the increment is to an address that is not valid. It hasn't yet been allocated, for example, by the operating system. Now, if you come back and re-execute this instruction, the stack pointer has already been increased. So you're going to increase it again and then write. So this messes up your stack because it's kind of like, you know, it was increased once and then it was increased twice when we executed it again. Another example is code that has partial execution. So let's assume that you have this. I'm now talking about example 1 and example 2. So I have a bunch of instructions. The first one is a multiplication. It multiplies R1, R2, and then stores the result in R3. Sorry, it actually multiplies R2 and R3 and then puts the result back to R1. And then the second is a branch on the result of R1. So whatever R1 is, if it is not equal to 0, then I guess this is a check. It checks R1 and R2. If they're not equal, then we go to loop. And if they're equal, then we just continue to the next instruction. So now in almost all modern out-of-order processors, this branch is basically predicted before the result of R1 is identified. So what happens is that this multiplication is going to take time. So this is like I'm getting two, let's say, 64-bit registers, and I'm multiplying them to get R1. And this could take multiple cycles. Now, the result of this branch depends on that execution. So because I'm checking R1 and R4, right? Now, if I yet to know what R1 is, I cannot execute the branch. I have to wait and see what the result of R1 is. But if I really wait here, what's going to happen is I'm going to waste a lot of CPU cycles because I'm going to just wait, right? I can't go and execute next instruction because next instruction is either I'm going to jump to loop or I'm going to continue with this instruction. So where I'm going to go depends on what R1 is going to be, and R1 is going to take time to have it to have its final result. Now, in out of order execution, what happens is usually based on previous data on this particular branch, you make a guess. You guess that, okay, I think with 90%, this branch is going to be taken, or this branch is not going to be taken. So the hardware makes an informed prediction of the result of this branch. And based on that prediction, if it predicts that with high probability this branch is not going to be taken, we're not going to go to loop, then it starts executing the next instruction before R1 is known. Now, it starts executing it, but it doesn't really write the result in a specific register. So it starts doing it temporarily. Once the result of this branch is known, once R1 is calculated and the branch instruction is executed, then it either matches the prediction, in which case, good, we're good. We have already started the instruction, so everything is good. So now we're ahead of ourselves. We have done a lot of work that turned out to be correct. If not, if it turns out that the branch was actually taken and we have to go to loop, then sure, nothing bad happened. I just spent a bunch of cycles doing some dummy work that now I have to throw in trash, right? So it just ignores all the results of the instructions that it has executed in a predicted way, and then it goes back to loop and starts executing from there. No loss. So this is called out of order execution. This is what you have here. If you're taking any computer architecture class, you will know about these. Now, why am I spending time talking about these? Because the same thing that happened with this push instruction that we talked about could happen with this out of order instruction. So what if this load here that we executed in a by just predicting that this branch is not taken, what if this load causes an exception? What happens to the system? Because I might actually not even be having to execute this. Maybe I should have gone to loop, but then I started executing this load and it caused exception. The same could happen here, right? This is another example. So you're dividing R2 and R3, putting the result in R1, and then you have a load. So most of out of order execution, they say, well, this instruction and this instruction, these two instructions are totally unrelated. So the first one works with R1, R2, and R3. The second one works with R4 and R5. And these are completely independent registers. So I can reorder them and execute them out of order. Now that's fine, but what happens if this instruction leads to an exception, this load leads to page fault before this instruction is executed? What happens? If we come back, which instruction should we execute? Now, this whole thing raises, so the solution to this is basically precise exceptions. Now, if again you take any computer architecture class, probably advanced computer architecture class, I don't exactly know if this topic of precise exceptions are covered in our preliminary computer architecture class, but this is a topic of work in computer architecture. How can we actually implement precise exceptions, meaning that I want to have a pointer to the last instruction that I'm sure that has been executed correctly based on the program order, and any instruction that I'm executing by just predicting that I have to execute, or I'm executing out of order, they're going to be after this pointer. So this pointer is always pointing to the last instruction that I surely executed based on the program order. And as I, let's say with the example that we predicted that the branch is not taken and went and executed the load. So the pointer is pointing. So going back to this example, and let me clean this up. So the pointer, that pointer that I was talking, is probably looking at this instruction, any instruction before this multiplication. So all these instructions are retired. They have been executed correctly. And let's say I have started doing this instruction out of order, just predicted that this branch is not taken, and I took that instruction. So these instructions, these three, are not yet retired. So now, if I get an exception by this guy, I'm not going to go and execute that exception, because that exception is from an instruction that has yet to be retired. Because my retired, so this is the retired pointer, is pointing to an instruction above this instruction that caused exception, so I can ignore this exception. And I only take the exceptions that happened before this retired pointer. So that's the idea. So I'm always basically keeping track of instructions that have been retired, right? And so this allows me to do, out of order execution. That's still fine, right? Because I can still do that. It's not going to change my retired instructions. Let's go back to this example. Let's say it turns out that this branch was not taken. Then I can just simply update my retired pointer and then go here, like jump, because I have been executing these instructions out of order. Now I can just jump to them. And then if I realize that this guy is causing an exception, then by the time that I update my retired pointer, then I can take that exception. So so basically, this bullet says that we only take exceptions for the instructions that are retired, and we ignore exceptions that are caused by instructions that are not retired. And the hardware, by some magic, will make sure that the instructions that have been executing out of order are not going to change the architectural state of my processor. Basically, they're not going to change the registers. They're not going to go and write to memory or read from memory. So they're going to read or write to some temporary storage without changing the actual registers and actual memory, which is what is important to the user. So basically, at the end of the day, this is how it's going to be. So the user executes instructions. At some point, a faulty instruction causes an exception. Then we go to the operating system. We take care of that exception. Then we're going to go back to the same instruction that caused the exception, and then this cycle is going to continue. Even if I have executed after this some other instructions, I don't care about those, because the hardware is going to make sure that they're not going to change the state of the processor by some magic hardware techniques, which is not a topic for us to talk about. But if you're interested, it actually happens in ROB, out of buffer, out of order register file, but we're not going to talk about that. Okay. So going back to the discussion we had, the TLBs have improved our performance dramatically, because we're just looking at the cached translations. Now, you might ask, okay, what if I want more performance improvement? Well, with one TLB, if you miss in TLB, you're going to go to do a page table walk. And that page table walk is very expensive. right? Like you have to go and look at 4 different page tables to eventually translate. Now, what you could do is to just put the same way that we had first level cache, second level cache, and then last level cache. You can have multi levels of TLBs. You can have first level TLB, you can have second level TLB, third level TLB, and then eventually go to your page table walk, right? So you can have multi-level TLBs. That's an idea that most of high performance processors in today's commercial processors do. So if you miss in first level TLB, instead of going and doing a page table walk, you're going to go to your second level TLB and see if the address is translated there. And if you miss there, you're going to go to your third level TLB. And if you miss there, then eventually you might actually go and do a page table walk. It's very often, I mean, I've seen 2-level TLBs very frequently. I don't remember seeing 3 levels of TLB, but 2 I have definitely seen in commercial processors. Obviously, adding more TLBs means adding more hardware and consuming more power and slowing down because of that. But then the speed up that you get could justify. It's kind of like adding caches. Okay. So to go a step even further, we could do one more thing. We could also use virtually addressed caches. Now, when we started this lecture on caches, I don't actually want to go back to my slides, but we talked about this idea of first level cache, second level cache, and last level cache. They're addressed using physical address. So when we're tagging, for example, in our cache, we're going to use the physical address of the block. Now, this means that in order for us to go to our cache, we first need the translation of the address, right? So basically, I need to translate my virtual address to physical address to then be able to go to my first level cache, and then second level cache, and then third level cache, and then eventually go to my memory, right? So that's basically what we have talked about. Now, one thing that we can do is to just have a cache that we're going to call virtually addressed cache. And in this cache, we're going to use the virtual address to tag our data. So instead of using the physical address to tag data, we're going to use the virtual address to tag data. So this is the best we could do, right? So I don't even need to translate anymore my virtual address to physical address. If I hit in this virtually cached, if I hit, it means that I have the data. So I don't need to do anything. If I miss in this one, if the data is not here, then I go and seek translation of my virtual to physical. And then, this means that I'm going to go to my TLB and see if I have the translation. If I don't, then I go to my page table. Eventually, I get my physical address. Once I have my physical address, then I go to physical memory. So this is going to give us a lot of a speed up, because it eliminates the need for translating the virtual to physical address altogether, right? So if you hit in this one, it's the best that could happen to you. It speeds up your execution. Now, it's not as rosy as this. So this having virtually addressed cache is going to cause problems. Now, the problem happens when you have synonyms. So we have talked about homonyms. Now, here comes synonyms. What are synonyms? So synonyms are different virtual addresses that are mapped to the same physical address. Now, this could happen in many different scenarios. One example is when you do memory map. So within the same process, if you memory map the same file twice, so if you remember, the idea of memory map was to get a file, bring the file in memory, and then map this file to virtual address space of the process so that the process can read and write from and to this file using just load and store instead of doing read and write system calls to read and write from this file. We can do load and store to memory, and that's the idea behind memory map. That's very fast. If you remember, the downside was that whatever you write, it's going to be in memory, so it's not going to go to your permanent storage. So at some frequency, you have to flush it to your permanent storage, because otherwise, if you get a power outage, then all your updates are gone. But now, what happens if you do memory map of the same file twice? So what happens is, the first time you do a memory map, this is virtual address space of process P1, right? And then let's say this is the physical memory, and this is virtual memory. So the operating system brings this file here. So this is file A, for example, and then it maps it to somewhere in the virtual address space of this guy. And then the mapping happens. So operating system maps this file to a certain address space of this this process. Let's say address space from VA0 to VA1 goes for this particular address. Now, let's say the program, for whatever reason, does another memory map. So it calls memory map of the same file again. Now, the operating system is not going to make another copy of the file in memory because the file already exists. So what happens is that the operating system is going to map a separate virtual address space, V0 prime and V1 prime. And both of them are going to be pointing to the same physical address range. Now, what has happened is I have two virtual ranges in the same process being mapped to the same physical address. So this is what synonym means. I have different virtual addresses mapped to the same physical address within the same process. So this should happen within the same virtual address space, because from different address spaces, that would be homonyms, which we have seen, and that's fine. That we talked about, dealing with that problem was to add the process ID. But with this one, both of these two virtual addresses are from the same virtual address space. They have the same PID. Now, why is this going to cause me a problem? It's going to cause an aliasing problem. And what that means is, well, if you're caching using virtual address, then here is my virtually addressed cache. So this is virtually addressed cache. Now, let's say this address and this address. So let's say VX and VX prime. Both of them are mapped to the same physical. Now they might be mapped to two different blocks because they have different virtual addresses. So there is a chance that they are cached in two different blocks in my virtually addressed cache. Now, both of them have the same data. So both of them have D0. Let's say I read once from VX and once from VX prime, and both of them are cached. So first of all, the first problem here is that I'm caching the same data twice. Because in virtually addressed cache, I don't know that these two virtual addresses are mapped to the same physical address because I don't have the physical address. Now, the second problem is, what happens if I change one of them? So what happens if I do a store on this VX with some new data D1, and then later on read from VX prime? What happens to this read? Well, this read is going to look at this cache block. This store is going to change this guy. And what happens is this read is going to give me a D0, whereas in reality, I should have had D1 because I wrote to this address D1. And this is a problem, right? This is aliasing problem. Now, one way to solve this problem is to tag our add a tag. So with homonyms, the solution was to tag your entries with the process ID. For synonyms, you need to tag your blocks with physical address. So now here comes the irony of this. We actually had these virtual addresses to get rid of physical address. But really, with synonyms, we can't get rid of it. We need to tag our blocks with the physical address. Otherwise, there is no way you can distinguish between these two blocks. And this problem will happen. Now, there is a way to basically kind of first use your virtual address and get your data, and then in parallel, start translating your virtual address to physical address, and then eventually check that, you know, the data that you read or write to was a correct one. So you can do these in parallel to get some speed up, right? So that's one thing that could happen. Now, the synonym problem happens in any hardware structure that you're using just virtual address. So this could happen anywhere. It's not just this virtually addressed caches. Anywhere, any hardware that you're using virtual address. For example, one thing that could happen is in your store buffer. So again, for those of you who have taken any computer architecture course, you should know about store buffer. And usually store buffers use virtual address. And again, this is going to happen because you might have two virtual addresses that are mapped to the same physical address, and you will have a problem. So you will need to use virtually indexed, physically tagged technique to get rid of it, which is kind of like, you know, making the benefits of just using virtual address go away to some extent. It doesn't go away completely because we can do them in parallel, right? We can access our virtually addressed cache and then in parallel do the translation. Instead of first waiting for the translation to then go to my cache, I'm doing it in parallel. I go to my cache first using my virtual address, and in parallel, I start translating to physical. And then at the end, once I have the physical and once I have the data, I check to see if the data I got, the tag for this matches my physical address tag. And if so, then I'm fine. So it's kind of like making it from sequential to first do the address translation and then go to cache. We make it in parallel, which is where we get the speed up. Okay. Right. So I've already actually discussed memory mapped files. So I'm gonna just skip over this slide. We've already talked about it. Okay, so to put everything together, everything that we talked about, to put them all together, let's look at this address translation one more time. So we're going to get a virtual address. We're going to divide it to offset virtual page number 1, virtual page number 2, or virtual page index 1, virtual page index 2. So we're going to use the first one to index into the page table level 1. Then we get a pointer to the page table, use the second part to index into this one. Then we get a physical page number, add the offset, and we get our page. Now, to speed this up, we added TLB. So with TLB, we don't do the page walk. So we just go to the TLB and see if we have translated the address already, so that we don't need to do the page walk. So that's the idea of TLB. Then we added physically address caches. So these are the caches that we're going to use the physical address, right? And then divide the physical address to tag, index, and byte select. And then go to our cache instead of going to memory. So this is another speed up we talked about, just caching. And then eventually we added virtual cache. So instead of, this is where the physical cache happens. After you have the physical address, you can go to physically tagged caches. So we also added this virtually address tags, virtually address caches to speed this up one extra level. And that's pretty much it. Now this is a good point to stop and answer the question. So do we need page tables from virtual to RAM and virtual to disk? Yes, so let's talk about this in the next lecture. So next lecture is about paging, and you're right. So when you actually do swap a page to disk, then you also want to know where in disk this page is. Now, most operating systems use internal data structures to track where the page is in the disk. But sometimes you could use your page table entry. So if you remember when we were looking at page table entry, was it here, or I think it was in the previous slide. So this is a great question. That's why I'm spending some time. So by the way, actually, I realized that I had a typo in my slides. Here there is a typo that actually occurs in a lot of slides. So first, let me go up here. So I have updated. So these are the oldest slides that I had. I have updated these slides. So please download the updated version. So this needed another 0 here. So for some reason, I had only 3 zeros here. It has to be 4 zeros. So, and then here, this number is correct, but then this number is wrong. So this should be 1000, and then 0000, which is 0x80. So this is another typo. I realized this later on, and I have updated the slide. So make sure that you download the latest version, which is just a fix that I just explained. Now, going back to what we were discussing, page table entry. If you remember here, I had these reserved and software bits here in my page table entry. Sometimes operating systems use these bits to store. So this physical number is basically the address to in the physical memory. Now, if you have moved this page to disk, definitely the operating system can store the tracking information inside its own data structures. Remember, this PTE is in hardware, right? But you could also use the PTE to store that data. So you could potentially use these bits to have some information about where you put the page. So this is extra hardware available to you to do the translation. But yes, so to go back to the question you asked, with regard to page tables, if what you mean is the hardware page table, it only has, the page table number. And if this page has been moved to the disk, then this valid bit is 0. So it's invalid. Now, when this happens, the hardware will notice that this page is invalid, and it will raise an exception. Now we're going to go to software. We're going to invoke kernel handler. Now, kernel probably internally has a track of where this page is. So now the kernel is going to go to the disk, bring this page back, then potentially maybe change the physical page number. Maybe the old page number is no longer available. So I'm going to map it to another page number, and I'm going to update this page table entry and then make this valid. Now, in terms of, where that information is about the tracking in the disk, as I said, it could be internal, or it could be using the page table entry bits for that. So hopefully that was a long answer to this short question. The other question that I got is, could you still end up with synonyms across multiple processes? For example, if process A shares memory with process B and one updates some shared memory, won't we end up with the same problem? Not necessarily, right? Because the problem won't happen in virtually addressed caches, right? Because if process A changes something and it changes its virtual cache, when you context switch, you can just flush this cache to memory and give process B an empty cache. So this will not happen because the virtual address is no longer a valid entry to be used for this cache. So you probably want to, when you do a context switch, you want to flush this cache to memory and then give the next process an empty slate, so that this problem never happens. So between process, what I'm trying to say is, between processes, the solution is easy. You just flush your cache so that this problem never happens. Within the same process, though, the problem is difficult to resolve, and that's where we need to use physical address to tag our blocks. Okay. Let's go back to okay, so going back to, yep. Now, to just show you all the discussions that we had, TLB sits here, right? Now we could also, if the actual page table is in memory, the TLB is very close to the processor. It's as close as your registers are. Now you could actually cache your page table entries, the address translation, right? Because it's like any other data in your memory that can be cached in L3, L2, and L1. You can also cache your page table entries. So if you miss in TLB, so if you go to your TLB and you miss, you have to go and fetch the page table entry. Now, where is it? Well, initially it's in memory, but if you cache it, then you can have your page table entries cached in L1, L2, and L3, so that this miss doesn't need to go to actual memory. It could actually hit in L1 or L2 or L3, and you can get your translation in those without going to the memory. So this is another speed up we get. So all these speed up, all these techniques that we're talking is to just make address translation overhead less and less and less. So all of these techniques will help us reduce the overhead of address translation. Now, let's do the access time for TLB. Just like any other cache, the average memory access is hit time in TLB plus miss ratio TLB times miss time TLB. Now, if the question is, TLB is like any cache, right? TLB is a cache. Now, we talked about set associativity for our caches. We had direct map cache, and then we had two-way set associative, four-way set associative, fully associative caches. Now, if you remember, direct cache was less flexible, but fast. Fully associative caches were it was really flexible, but slow. Now, if you look at this equation here, you know that this miss time in TLB is really high, because if you miss in TLB, you have to go and fetch the translation, which means 4 memory accesses. So this is really high. So your initial thought might be that I really want to bring this miss ratio down. I really want to hit in the cache, and I want to have a really low miss ratio. So now you have two options. Should you do a direct map cache, or should you have associativity? Now, if you go with direct map cache, you're going to get a lot of conflict misses, because obviously each one of them is mapped to a certain cache block. So direct map gives you high conflict misses. So if you have conflict misses, this means that your miss ratio is going to go up. So conflict miss means that you're going to get a miss, and it's going to make your miss ratio go up. And if your miss ratio goes up, your miss time will show up. So if you go with direct map, you're going to bring your hit time down, but you're going to increase your miss ratio. And if your miss ratio goes up, this miss time is going to show up and hit you really hard. So instead, you might actually go with fully associative cache, which is usually and typically the case. TLBs have fully associative caches. Now, this means that you're going to have higher hit time, because your cache is more, the TLB is more complicated because it's fully associative, so it needs more hardware. So you're going to pay higher hit time, but at least your miss ratio is going to be low. So let me actually clean this up a little bit and have it in one place. So with direct map, your hit time is low, your miss ratio is high. With fully associative, your hit time is high, but your miss ratio is down. Now, which one to pick? Well, this one, because the miss ratio is really high, if this miss time is really high, like a really big number, then bringing the miss ratio down is more important than incurring a hit time. So that's why you usually pick this one, because this portion at least would be less expensive, because you bring your miss ratio down. It's fine to pay some cost with hit time. Okay, now, does TLB always improve my performance? Now, TLB is like any other cache. It would only work if you have temporal or spatial locality. So if you don't have locality, then TLB is not going to be helpful. Now, when do you get to have locality? You will get locality if you're going to use the same address again and again. Now, TLB is usually very small. TLB is not big, so you can't have a lot of addresses cached. Now, if your program goes over a huge range of virtual address, then the chances are that you're not going to see the same address again and again. So, here is one example. Let's say your display. Let's say you have an HD display, high definition display. These displays have really large buffers because you're going through a lot of pixels for every rendering of your page. So you go through a lot of data every time. Now, this data is somewhere in memory, right? So you're going to go through a lot of data. For example, here is a 4K display with 34 bits per pixel, and this is the number of pixels you have in your entire display. So that's how much data you need per rendering of your page. Now, if you have 4 kilobyte pages, this means that you have 100. So this means that you have 12K pages. So you need to translate 12K different virtual address to physical address. Now, a TLB is very small. It can just fit in a max 256 entries. Now, if you need to translate 12K pages, you're not going to hit in TLB, because by the time you're back to the first address, you have cached everything and you have thrown away that cached address. So cases like this mean that TLB might not work. Now, one way to address this issue is to use what is called superpage. If you remember, when we were talking about multi-level page tables, I purposefully talked about how much memory a page table, a page has. That was 4K, and then page table level 1 was covering 2 megabyte, and then page level 2 was covering 1 gigabyte, meaning that each page table entry level 2. So if I have page table level 1, page table level 2, page table level 3, and page table level 4, and eventually my page. So this guy points to this guy points to this guy, so this one is 4K. Now, this whole page is going to cover 2 megabyte. And here, you're going to cover 1 gigabyte. So any pointer here, any pointer in page table level 2 could potentially cover 2 GB of data. Now, this is what is called a super page. Now, if you look at the page table, we can add an indicator that says this entry here is the super page. And a super page means don't go to another page, just use this as a pointer to point to a page. So basically bypass these other pages and use that address to get 1 GB of data here. But then all these pages have to be contiguous because I'm using the same address for all of them. So all of them have to be contiguous. So this is the idea of a super page. Now, if I do that, then I only need one address for all this 1 GB. Whereas previously I needed a single address for each page. So a single address for every 4 KB. Now this one gives me one address for 1 GB. And this is a super page, which consists of a bunch of pages. So I can have a super page of 2 MB. I can have a super page of 1 GB, and I can have a super page of 2 to 9 times 1 GB, which nobody wants this because this is going to be bigger than any physical page. But a super page of 1 GB is can be used. A super page of, so if I want to use page table level 3, this guy could just bypass level 4 and point to a 2 MB super page. So I can have 2 MB super pages, I can have 1 GB super pages, or I can have just my regular pages, which are 4K. So this will allow us to not need a lot of address translation. We can just have one address translation for a huge range of physical addresses. And if we do this, then TLB is going to be fine, right? So in the example of the display, I can just put all those pages for my display in a contiguous region of physical memory, and then define a super page, and then just need one address translation for the entire thing. Okay, so the last topic I want to discuss is the topic of how this virtual memory connects to where things are in Linux. So in Linux, what they did was they added kernel addresses to the virtual space of every single process. So basically, this restricts processes in terms of their usage for their virtual address. We already saw that in a 64-bit system, you can just go all the way to from 0 to 2 to 48. Now, in Linux, so in 32-bit systems, 1 GB of your address space was reserved for kernel, so the processes cannot have access to that range of their virtual address space. In 64-bit systems, this has been increased to 128 TB of your address space you cannot access because it's reserved for kernel. So if you access any virtual address within this range, you're going to get a page fault because you don't have access to them. In 32-bit system, any virtual address within the range of C00000 to FFFFFF is going to be causing page fault because it's kernel space. Now you might ask, why do I need to map kernel to processes? The reason is on system calls or on interrupt handlers, we're going to go and execute kernel code. And when we're doing kernel code, the kernel code uses its kernel virtual address space. Now, when it comes to TLBs, if I'm running a system call handler, or if I'm running a interrupt handler, and I need to do a translation of addresses, if the translation is not in my TLB, it's going to slow me down a lot, as we saw. That was the whole idea of having TLB. Now, if the TLB is full with user data, with user address translation, and now I'm going to go to kernel and do some translation, none of them are going to be in TLB because the TLB is full of whatever user has done. And then I'm going to, let's say I'm going to context switch to another user, and then that other user is going to fill up the TLB. And again, I'm going to do a system call handler, and again, I have nothing in TLB. So every time I'm going to run the system call handler or interrupt handler or anything with regard to kernel, I'm going to be missing in TLB. To avoid that, I make sure that this range of everybody, every process's virtual address space is allocated to kernel. So one time that you use and fill up the TLB with the virtual addresses with regard to kernel, if you context switch and start running someone else, and they also need a system call or interrupt handler, you already will have the data in your TLB, the translations, because both of these two processes use this same range for kernel functions. So if one of them caches it in TLB, the other one can use it. So this will speed up a lot the kernel code execution. Now, this is the plus which kind of motivated this mapping. Now, on the downside, I think the Meltdown and the Spectre attacks, which I think it was like 2017, if I'm not mistaken, 2018, showed that this mapping has huge security risks. So I guess I won't be having time. So let's do this. Let me finish these slides, and then I'll come back to these attacks after the lecture is done. So if you're interested, you can stick around, and I will talk a little bit about these attacks. But if not, we're gonna just move on with this. Okay, so actually good. So we're done with these slides. So I can just talk about these attacks. So if I go over time, you can just log off. Now, I want to explain why this could have security risk. So the first attack that I'm going to talk about is Meltdown Attack. And I need, for you to understand this attack, I need to give you some background. Now, we talked about this out of order execution today. And I also talked about this, the idea of having branches. So if you remembered, we had that instruction that was multiplying and then branch not equal R1, R4, branch to loop, and then I had a load, right? And at that point, I discussed the fact that we really don't want to wait for this branch, for the result of this branch. So most of out-of-order execution processors have this speculative execution. So with a speculative execution, you make a prediction about the branch, and you start executing whatever your prediction tells you. Now, this a speculative execution doesn't change your actual registers or your memory. They change your TLB, they could change your cache, but they don't change your architectural state. That's why they're safe. If an exception happens, you can throw away all the temporal logic that you have because your registers and your memory are safe. They haven't changed. Now, The problem, though, so this is basically all the things that we talked about. You can start executing, and then if you realize that you mispredicted this branch, you roll back. And a roll back means that you're going to discard all the things that you did speculatively because they didn't change your registers, and then you're going to go back to where the actual branch says once it's retired. You go there and start executing from there, and you haven't missed anything. So this is the background. Now, how could this be bad when you have this shared address space between kernel and user? Now, at the surface of it, having this sharing is not problematic, because if my user wants to access the kernel stuff, I'm going to get a page fault because the user doesn't have access to this memory. And I can get that with this. If you remember with page table entry, it had a bit that was user or kernel. So I can set this bit for kernel, and then if the user wants it, I'm going to have a page fault. You didn't have access to this page. That's what the idea was. But then mixing this with out of order execution causes problem. Here is how. So Meltdown was announced in 2018. Actually, they figured it out before they announced it because it was very serious. So they reached out to Intel, and they told Intel that almost all your processors have this issue, and it's very serious. But then shortly after Intel was notified, they actually had to notify the public, so it went public. It also affected IBM. It also affected ARM processors, but it didn't affect AMD processors. So AMD processors are assumed to be safe with Meltdown Attack. Now, here's how the attack works. So I'm going to have a character array of 256 entries. So this is because I have 256 different characters, because each character is 8 bytes. So 2 to 8, that's 256 different characters you can have. Now, the reason I'm multiplying it by this big number is because I don't want these characters to be on the same block. Because if you remember, I said a single block is more than 1 byte. So I'm multiplying it with this large number so that I make sure that so I want to make sure that this array 0 and then array 1 times 4096, and then array 2 times 4096. So these are now in different blocks because I have enough bytes here to make sure that these are not in the same block. Because if they're in the same block, then I have a problem, because cache works with blocks. I want each one of these this one, and then all the way to 255 times 4096. So now I'm making sure that each one of these is in a separate block. So I'm not going to care about anything in between from 0 to 4096. I don't care about those. Or from 1 times 4096 to 2096. I don't care about any of those. I only care about these aligned arrays. Okay, so this assumes that there is a function that could flush your cache. So there are a lot of work on this, how this function works. So one thing you could do is to just write to certain range of addresses to make sure that your cache is going to be flushed. But I'm not going to spend time on this. So let's assume that there is some way to make sure that your cache is flushed. There is nothing in your cache. Okay. Now I'm going to try. I'm going to do this. So this try is not your usual try catch. Try catch. It's basically it's kind of like working with signal handler. If you remember from early slides where we were talking about processes, we talked about the idea of handling signals. So when page fault happens, the operating system sends you a SEGV, which is an illegal access, right? This is a signal, and if you don't define it, it's going to terminate your process. You could define it. So you could, if you remember, we talked about telling the operating system that if this signal is sent to me, then run this function, right? So you're defining a signal handler. So this makes sure that your program doesn't crash when it accesses something illegal, right? Okay, so there's a technique to handle signals, and we didn't talk about how you can handle signals. There was an example I showed you to define a signal handler, but let's assume that you're defining this signal handler for SEGB. Now, what am I going to do? So I'm going to access a kernel address, an address that is illegal to me. And when this instruction is executed, it's going to give me a segmentation fault because I didn't have access to this, right? Now, the next instruction is to cache. So to go to this array, whatever this result is, go and read this particular block in my cache, right? So whatever result is, read it. Now, obviously, if my instructions were executed in the same order, I shouldn't be able to execute this instruction, right? Because, well, result should not be there because I shouldn't be able to read anything in kernel address space. So this instruction should not retire. This instruction should not happen. So I should get a segmentation fault, and then it should crash, for example, right? Now, if in modern processors, these instructions happen out of order, what could happen? Now, this part, let me remove this here. So this instruction, this single instruction here, is going to be divided into micro instructions. What is a micro instruction? So why do we need a micro instruction? Well, this single instruction, which is a read, the hardware has to do a lot of stuff. So it has to go to that memory. It has to also check the page table to see the access was granted or not. So this single read means a lot of work in hardware. So go read it, check the page table access to see if this has access or not. Maybe this is, this particular case is a character, but if it was multiple characters, then you might actually go to memory multiple times. So this has multiple pieces. Now, the hardware could execute these out of order. So what could happen is you could first read the address, then go and check the access. And if the access is not granted, then you can raise an exception. Now, this next instruction could be executed before you check the access to see, oh, this was not granted. Now, if you do that, what's going to happen is you're going to go and change your cache. You're going to cache the result in your first level cache, for example. But then caching is okay because cache is not in your architecture. So if you realize later on that this was not granted, everything is fine because you haven't changed any register, you haven't changed any memory. So you can just execute the segmentation signal. And then your process could start running here. Now, what has happened is you have changed your microarchitecture, you have changed your cache. Now, this particular block in your cache has changed. How can I use this information? I can now go through all the characters possible, go through all these blocks from 0 to 255 and read them. I can just read array I times 4096 and I can time this instruction. I can time this. I can see how long it takes for me to read this address. Now, if my cache was flushed, then all of them should go to memory, but the one that I changed and brought to my cache. So the only one that here I executed out of order is now in my cache. So that particular read will be so fast because I'm going to go to my cache and come back. The rest of them are going to go to memory and come back. So if I have a way to time how long it takes for this read to happen, for a particular I, this read is going to be really fast. And for the rest of the I's, this read is going to be slow because they're going to go to memory. And for that particular I actually have read the result because I changed the block for that particular result in my cache. So if I can get the fast cache access or fast memory access, I have found the character that was stored in my kernel space. So they actually showed it takes time, but the code is actually available on Meltdown website. You can actually read the entire kernel address space by just this hack. So you can just read every single address in the kernel address space. Now, there are patches to fix this meltdown. So one thing that changed and happened because of this was that the Linux started shrinking its address space. So if you look at recent versions of the kernel, this has changed. So we don't store the entire kernel address space in each process. We only store a very small range. And also the kernel, every time it context switches, it flushes TLB. So that this doesn't happen, right? It gives you a slowdown of, I think, 8 times a slowdown. As I discussed, this means that every single interrupt handler and system call handler will have to do the translation, but at least it's safe, right? So it could have, these patches will kind of solve the meltdown issue, but they have high overhead. Now, unfortunately, after meltdown, there was another security risk caused by out-of-order execution that was called a Spectre. Now, a Spectre actually impacted all the, so with the meltdown, AMD processors were not impacted. With a Spectre, even AMD processors were impacted. And with a Spectre, there is no software solution. So there is no patch. The kernel cannot do anything, basically. And almost all of our systems, certainly all the processors you bought before 2008 has the issue with the Spectre. So an adversary can basically read your entire physical address space because of out of order execution. I definitely don't have any time to talk about Spectre. So that's pretty much it. So yep, that's it with this. Sorry that I went over time. I think it's worth talking about security at least a little bit. We don't get to talk about it much, but anyhow. So thank you for sticking around, and thank you for watching this. Take care, be safe. We'll talk to you next week. Bye.